Thank you, Misha, for the introduction. Thank you to the organizers for having me here. I've been at IPAM several times over many years, and it's always a real pleasure being here. Having said that, I'm perhaps a bit of an outsider to the deep learning field. I'm learning every day here from every talk. I'm learning a lot. And the topic of the workshop is really quite taxing because we have both theory and applications. And I decided to tell you a little bit about some theory and some applications. The theory is not really deep, in the deep learning sense. I guess in the language I barely have one layer. But I hope you will find it somewhat interesting anyways. And there are multiple co-authors, and I will be specifying their contribution to the different works that I'm going to talk about as I go along. They're sort of clustered by theory. Yan Tao, who is a PhD student of mine in math, and applications with Natalia Trajanova in their lab in the biomechanical engineering school at Hopkins. All right, so the first part, right off the bat, is a classic statistical problem, the problem of regression, predicting the value of the function. So we're giving pairs of input and outputs. The inputs are in R capital D. My capital D is big, right? It's a high-dimensional problem, and the Y's are the values of the function we're trying to predict. And classical assumptions, the inputs are distributed, independent, with some distribution rho. And the Y's are the values of the function may be corrupted by noise. Maybe the function has some regularity assumption, just for simplicity, say, as S derivatives continues. This S can be non-integer, so this can be in the Holder sense. And the noise is maybe Gaussian or sub-Gaussian. And of course, the goal is, given these inputs, to produce some estimator of F. So some function that is close to F in L2 rho. Rho is the measure on the axis. And I think we are all well aware of some roadblocks towards efficiently learning these high-dimensional functions. The course of dimensionality implies in this situation that if we have no further assumptions on rho and on knowing that the function is just yes, there are no algorithms that can, there are no estimators even, just constructed mathematically without any algorithm, that can achieve a rate which is better than n to the minus s over 2s plus d. And that is bad news because if s is a fixed integer independent of the dimension, say 1, a function, Lipschitz function, this exponent scales like n to the minus 1 over capital D. So if you want to achieve accuracy epsilon, you need about 1 over epsilon to the d points. So a number of points which is exponential in the dimension with respect to the accuracy that you want to achieve. All right, so we can learn and predict functions in high dimensions, outcomes, and again, this is in the minimax sense. So it's an adversarial setup in a way. So one can say, well, maybe there are some adaptive techniques that when f has some special properties, this rate can be beaten. And so which kind of properties f might have so that we avoid the curse of dimensionality. And here is a couple of examples which go in different directions. One direction could be the following. So there is some low-dimensional structure in the form of the data being supported on a low-dimensional manifold. And if the low-dimensional manifold has a dimension small d, which is much smaller than the capital D, perhaps we can take advantage of this concentration of rho and do better. And that is in fact the case. There are several algorithms that can beat the curse of dimensionality in this setting. And you can achieve a rate if you know that the function is yes, which is like the one above in the course of dimensionality, but the dimension now is the intrinsic dimension of the manifold. So big win when small d is much smaller than big D.
So you're saying that they're adaptive, so they don't need to...
You don't need to know the manifold.
You don't need to know D either, little d? Or do you know?
So there are estimators for D. That's one of the things I'm also passionate about that we have developed, but many other people have also done work on estimating the small d given data on the manifold. And then there is work that shows that if you use a variety of techniques, you could do this with kernel methods, for example, and you would achieve a rate that depends only on the intrinsic dimension small d. And maybe it's important to remark that we also care about how fast the algorithms run. And so the algorithms that we use to attack this problem run in time and log n. And there is a curse of dimensionality in the algorithms in terms of a constant, which is exponential in the intrinsic dimension. So, but when n is very large, and if small d is not unreasonable, I think this is near optimal. You can also have other types of spatial structure. This dates back at least 50 or 60 years. So for example, you could have a function, a capital F of x, that is in compositional form. It's g of ax. So A is a map that takes capital D, it's a linear map, that takes capital D dimensions down to small d dimensions. And so ax is small d dimensional, and G is defined on a small d dimensional subspace. And so here you could, of course, if you knew A, then you would be working small d dimensions, and you will avoid the curse of dimensionality of the ambient dimension. But the problem is I don't know G, I don't know A. Does this assumption of compositionality help me avoid the curse of dimensionality? And so this is called the multi-index model, and I'll talk more about it later. Other types of models that could, and in fact do, avoid the curse of dimensionality are additive models, where your function f is decomposed as a sum of one-dimensional functions. And so in this case, you know the coordinates in which you have one-dimensional things. You only need to estimate the fi, and this is relatively easy. Algorithmically, I would claim there are still maybe possible improvements. And I'm not going to go really through these slides, but just to give you a flavor of some of the things that I like, this is work that we did with Wenjin Liao and Stefano Vigogna, now respectively at Georgia Tech and University of Rome, where we sort of push the boundary of this learning a function on a manifold when you don't know the manifold, when you don't know the function, and the data is distributed on or very close to the manifold. Again, I'm not going to go through the details, but the basic idea is that you learn an approximation to the manifold at different scales. You approximate the manifold by chopping it up into pieces. It's all multi-scale. On each piece, you approximate a tangent space. And on each approximate tangent space, you learn an approximation to your function. Now, this tangent space is multi-dimensional, and so this estimation is done in small d dimensions. And then you have to choose the correct scale at which to do this multi-scale decomposition. So you pick a scale. And in fact, maybe you want to pick the scale depending on the smoothness of the manifold and the smoothness of the function. So we're particularly interested here in functions that might be very smooth in some regions, but then they're wild in other regions. And so when they're very smooth, you want to gain sample strength by picking large pieces. And when it's not smooth, you want to adapt and pick smaller pieces. These games are well understood in low-dimensional equilibrium settings, and here we translate them to a manifold. And so the theorems that we prove are sort of universal and adaptive in the sense that the function class that we consider is very large, much larger than CS. It contains functions, again, with different degrees of smoothness in different regions. We don't know their degree of smoothness and in which regions they're smoother or less smooth. And we construct adaptive algorithms that achieve near optimal rate. The near optimal is just because of this log n, with minimal knowledge about all of these properties, including the manifold and the local regularity of the function. So that's just an ad for that work. I don't expect you to have even read through this. All right, so going back to structure functions and this compositional structure, so we talked about the multi-index model. So f of x is g of ax, where a is linear and does this dimension reduction. And the simplest instance of that is, of course, when the dimension reduction achieved by a is maximal. So when small d is just equal to 1. And that's called the single index model. Okay, the single index refers to a single vector v, right? My matrix A now is just rank 1, so it's just projecting in one direction. Let's call that v. And x inner product of v is just a one-dimensional number, and g is a one-dimensional function. And of course, one is interested in the case, I guess the more interesting problem is trying to estimate v, but really, the full problem is estimating both v and g. All right. And so lots of work has been happening in this direction for at least 30 years, I would say, if not longer. And there are many results, and I'm not going to go too much into the details because maybe you're not that interested in the single index model, but it's a really fun toy problem, and I think there are, even now, there is room for discussion for improving some of these results. But the way things, the narrative, yes?
Yeah. I'm personally very interested in single index models.
Thank you for saying that. I thought that everything had been done there back in maybe 2016 or 17 when I started reading the corresponding papers. And then I started, and I want to build on that. And then I started seeing what I consider sort of holes, either in the theory or in the computational aspect of these algorithms, where maybe the theory gives you estimators that defeat the course of dimensionality, but the corresponding algorithms are exponential in the dimension, or vice versa, a really fast algorithm, but then no guarantee that they actually converge to the right answer. And so I was dissatisfied and started working a little bit on this. But the standard story is that you can learn V at a rate which is the parametric rate, 1 over square root of n, so really can't beat that. And at least when G is known. And if G is not known, then I think the discussion is a little bit more complicated, but I think most people will say that this is an essentially solved problem. And albeit, usually with strong conditions on both the distribution of X, essentially X Gaussian or with an elliptical distribution. We'll see why the distribution of X can be important in this problem. And maybe assumptions on G. G monotone is a popular assumption, I guess. Which is, of course, strong and something that we would like to get rid of. But so basic observations about the single index model, the most basic observation of all is that, okay, we don't know V or we don't know A in the case of multi-index model. Well, if we take the gradient of F, that's just proportional to A, right? So A comes out. So if you could estimate the gradient, you get an estimate of A. Of course, estimating the gradient of F is as hard as estimating F. We're in very high dimension. But the point is that this gradient, yes, it's a function of X, but only through this number, right? And so if you could get noisy estimates of gradient of F at many, many, many different points, then since the matrix part of the gradient is constant, then you can perhaps denoise those noisy observations of the gradient using all the samples everywhere and get a good estimate of A. So I call that gathering strength or from far away samples. And that is the motivation why you might be able to skip the course of dimensionality. Yes?
Quick question. So I can imagine two setups. One, I'm going to assume the data actually are from a single index model. And the other would be I want to look at the excess risk where I'm comparing myself to single index model predictions.
Yeah.
Yeah. The first of that feels like a classical statistical approach. Second of it feels more like a machine learning type
that's very good. Yes. That's right.
Which are you studying, and are both of those?
No, I'm going to consider the first, the easier case. Okay. So the single index model is actually correct. Albeit, it's an excellent, I think, direction to ask, if I restrict myself to 1 index or 2 index or 3 index, what's my best approximation within that constrained rank? So you're going to have a bias if the truth is not there, and doing the trade-off is interesting. And this has been explored in the literature. I could point to papers that do that, and I think it's very interesting. Because, of course, we usually won't believe that this holds correct. And another fundamental idea that I like very much is this old trick in statistics, which is called inverse regression. The idea is that, at least the way I think about this idea is that we like to partition things into smaller pieces so that the function becomes easier to approximate and so on. But we're in high dimensions, we have too many small pieces, and we should really construct pieces that are adapted to the problem. And in inverse regression, this is achieved in the following way. Instead of partitioning the x's, you partition the y's. So you take little intervals in the outputs, and you look at the pre-images. So you look at all the points such that f of x is equal to that y, or lands in that little interval. And this gives you an approximate level set of the function. And if you look at the single index model, the level sets of the function f are just hyperplanes with norma equal to v. The function changes all in the v direction, so all the level sets are just flat hyperplanes orthogonal to v. And that, in a certain sense, is the right metric with respect to which you should measure the distance between points. The correct metric is between 2 points in high dimension is really project them onto v and look at how far they are, because that's enough to learn the function f. And so if you look at these level sets, they're sort of equivalence classes for this metric. Okay, and so just a few years ago, we studied a single index model. This is joint work with Alessandro Lanteri and Stefano Bigogna in Torino and Rome, respectively, just as an exercise to learn more about this. And we came up with an estimator constructed by a simple algorithm that does the following. So first of all, it looks at, it slices the y's. It looks at the pre-images of those slices of y's. Those are hyperplanes of a certain thickness, depending on how thick the interval in the y's is. And in each of these slices, we can collect simple statistics. You know, these slices are high dimensional. We don't know where our direction V is. So we use moments, which scale reasonably low, order moments, which scale reasonably well with the dimension. And that's just the mean and the covariance matrix. And if these intervals in Y are sufficiently thin, when we pull them back under some assumptions on F that I'm going to go back to, we get a rather thin hyperplane. So the direction V is the smallest singular vector. And so we compute the mean, the smallest singular vector. And then this smallest singular vector is an estimate of the direction V. It's noisy because it's done only in one slice. But if you run through all the slices, you get different noisy estimates of the same vector because V is the same. So you average it out in the natural way. And then you project all your data into the line that you found, and you do local regression. And so this algorithm constructs an estimator, and what we can prove about the estimator is that it gives us the parametric rate for estimating V, and it gives us the optimal one-dimensional rate for estimating the function capital F, right? So the small d over here is 1, and that's what we get. Under suitable assumptions. Okay, you're going to ask about assumptions?
No, I'm
okay. Yeah.
So there is a classical algorithm, right? The sliced inverse regression. I just like how does?
Yes. So there are tons of algorithms in the paper. We have a big table with all of the algorithms that we know of, which guarantees are known. What's the runtime and what are the assumptions on the function f and so on. So that's a point of reference. So this idea of using slice inverse regression is not ours. Slice inverse regression, SIR, and so on use similar ideas. They don't use the smallest singular vector. They use, for example, something like the mean of the slice. And I'm going to show in a couple of slides, sorry, that can misbehave, for example. And also, they don't do the joint estimation. So I don't know if there is a theorem about any of those algorithms. So they typically focus on this part, but less on this part. I should also stress that this algorithm runs in log n with a constant which is not exponential in D, it's just a D squared. Now, suitable assumptions, again, I'm not going to go into there, but we do have assumptions both on the distribution rho and maybe even more taxing on the function f. We need f to be roughly monotone. So it needs to have a monotone trend. It can have oscillations, but overall, it should be kind of monotone. And that's a big assumption. Okay.
I've lost track of what capital D is. What's capital D?
Capital D is where the points are. And I apologize, but this is a capital D. Okay. That's why you're asking. I apologize. Yeah. Different notations in different papers. This is just single index. Yeah, because we do use the fact that the slices are really these thin hyperplanes orthogonal to V. In the multi-index model, this would be thick hem slices, because in the d-dimensional plane over here, the function can do whatever, but in the other dimension, it does not. So instead of being a flat slice, it would be a deformed slice, and this deformed slice can do a lot of things. And so multi-index is I consider it significantly harder than single index if you want to use inverse regression.
But the span of bottom eigenvalues, eigenvectors should still
should still. And we've done experiments, and you randomize, you collect many, you denoise, and we see it working, but we don't have a theorem. And I like guarantees on what they do, so we are holding off advertising that too much. Yes,
just wanted to make sure I understood. On the previous slide, you had a statement about the gradient of f(x) and saying that this is only the direction is independent of x. Is that statement also specific to a single index model?
No. So G prime of A of x is just a number because G is valued in R. And so the matrix A is shared between all of these matrices on the right-hand side.
But G prime is going to be a vector.
Oh, well, yeah, it's a gradient, but so this would be A times a small d-dimensional vector, and the matrix part is shared between all of these products, A, the vector. Yeah, yes, thank you. yeah, I said number before, but it's a gradient that varies. But think of it as it's almost a matrix estimation problem under many linear observations of the same matrix, right? Where the linear observations are given by these gradients of G at different locations. Thank you. All right. Okay, and of course we verify this numerically. So these are curves obtained by our algorithm as the dimension increases, say up to 100. The rate is always the same. This is done on a function that is going to show in a moment. These lines are just say for if you use a local method, KNN or local kernels. And this is for another function, which is a random monotone increasing Holder function. So here is why assumptions on rho are needed. So suppose these points are projected down. Well, let's even pretend that capital D is just 2 here for the sake of this example. This is the distribution of points. You see that the F is constant on level sets which are orthogonal to V. That's the black line. And one of the classical algorithms does computes the inverse slices and it computes the means. Those are the dots on the green curve. And we compute the blue vectors, which are centered at the mean, but also at the direction. And if you look at all the means, all the points on the blue dots on the green curve, and you do PCA of those, for example, you get a pretty good estimate of V. This is what SIR does, and there are variations of this as well. And if you do the average of the blue vectors that we compute, you get the same very good approximation to V. But if the distribution is very unbalanced with respect to V, so V is now in this direction and this is the distribution, when you compute the means corresponding to the dots on the green line, you can get an estimate of V which is completely wrong. While if you look at our directions, the blue, they're centered at their own points because they're centered at the means, and those are not along the line V, but they all point in a consistent direction of V. So some symmetries of rows are somewhat needed, but our algorithm is more robust than most to these sort of things. And this is one of the functions we estimate. I want to emphasize that this is also a multi-scale problem. We are slicing in Y to get our slices. Then as we get our slices and we discover estimates of V and we denoise them and we get our line, we project the points on that line and then we do local regression there. So there is also the scale of local regression. And in our algorithm, those are 2 parameters and the theorem tells us how to choose those parameters. And if you don't choose them wisely, you can do very poorly. So in the first row, we chose slices in Y which are too thick and we just get nothing. And over here, we fix a reasonable size of the slices in Y, and we change J, which is the scale of the little intervals in which we do regression after projecting onto the line. And of course, if those bins are too large, we get a over-smooth fit to the curve. If they're too small, we get a noisy version, and there is something which is just right. Yeah?
So in effect, you're trying to recover F and
V.
G
yeah.
and V.
G and V, yes.
Have you considered, or is it studied in literature like an improper version of this, where you assume that G and V are explaining the data, but you look for an estimate that ultimately want to get close in L2 again, but you're going to allow yourself more flexibility. You don't need to fit.
So you want to predict capital F well, but not necessarily in that form, absolutely. And for example, in my experience, this is what happens most of the time when you train a deep network on this. It will give exceptionally good results in predicting F, as good as our algorithm, at least for, didn't quite succeed in getting the correct rates as n goes to infinity, but I blame myself. But even for small n's, exceptional results in predicting capital F. But if you don't initialize and you train it really, really appropriately, the V is nowhere in sight in that neural network. Which is interesting.
You can say that neural network effectively learns V, right? If you look at actually the first layer of a neural, like of an ML.
It really depends on how you train it. So it can happen that you can get really good approximations of F with a neural network without V being anywhere in the network. You can also train it so that the network learns V, but you have to be very specific about how you train that network. You can train it not in those very specific ways, and the network still does very well, but it's in a way an improper model in the sense that it hasn't discovered G and V, but still predicts capital F really well.
I think that whenever you get good result, it learns V.
Okay, I would love to brainstorm about this. I mean, I think it's an important discussion to have.
Can I ask just to follow up on that? Like, in those models that learn to make good predictions but don't seem to find V, like if you took the gradient of those models, do you recover V? Or are you like approximating like
so if you look at your capital F is a good approximation, and its gradient is going to be in the V direction.
So it does learn V in that sense, at least.
Well, but that's the same sense in which my F depended on V. So, but the V, I mean, I'm fairly sure that I looked carefully enough at some experiments that I can see this V in any of the weights of a network if I don't train it, just right to reveal the V.
You take WW transposed, and that's very much aligned with V.
I think
Have you tried that?
Yes, but I think it depends on how you train the network. And so for the longest time, I would get really good predictions of capital F, but no W's. And then if I initialize and set up the network in a special way, then I can get the V out.
Quick. Oh.
Yeah.
So I'm just trying to sort of like envision a setting where so it looked like this monotonicity was a pretty necessary assumption, or is that
Which assumption again?
The fact that the function G is sort of like monotone. I'm sort of envisioning a situation where you have like a bowl-shaped curve, and when you look at the inverse image, you have disjoint hyperplanes.
That's right. So if F is not monotone, when you look, you slice in Y, you get a pre-image, you're going to get separate hyperplanes. And, maybe they seem pretty far away if you look at them when you project in the V direction, which you don't know and yet, right? And so you need to somehow separate these hyperplanes in high dimensions. And so we do some of that, but we don't have a theorem yet. And it seems a little bit delicate, right? I mean, the function goes up and down many times. Then, some of these hyperplanes are really close. Some of them are farther away. So there is, I think, a notion of complexity for the function, which is a little bit different from the usual ones that would govern success of this algorithm. And also, these observations, I should stress that they are conditioned on sticking to inverse regression methods. Some other method might not care at all. And there are, in fact, methods where they don't need to assume that F is monotone. On the other hand, I think the best that I know of those methods, at the very least, they have constants which are exponential in D. And if you have constants which are exponential in the algorithm, maybe it's not that useful. You can search a lot of the unisphere for V, for example, in a brute force fashion. So it's, I feel that it's still delicate there.
I was going to say, people were talking about estimating the gradient of the network, the neural network you learn, but if you're talking about just a guarantee of learning in L2, that's not going to tell you anything about derivatives converging, right?
That is true. So it is an additional fact.
Yeah.
But if you look at these gradients, they do approximate V.
Okay.
Yeah, that's right.
Yeah, but
Yeah, so some feature learning is happening, but it's not. I find that it's not always going all the way to the end and giving me the right thing. All right, so it's natural to ask, what happens for more general compositional model, right? So if F is G composed with H and H is nonlinear, right? Let's get out of the projections on linear subspaces or linear or single directions. And I think that in general, we cannot hope to avoid the curse of dimensionality. Maybe there is some hope if H is super, super smooth, capital D time differentiables with all the derivatives bounded. Those function spaces are very restrictive, of course. And there has been a lot of work in this direction, partially motivated by deep learning, but also by classical statistics in trying to avoid the curse of dimensionality. I mentioned here some of them. There are the deep compositional models by Suzuki and others, where they consider anisotropic Basel spaces. So these are functions that vary in a maybe small number of directions, and they are super smooth in the remaining ones. And the directions where the functions change is just small d, and in all the other capital D minus D directions, the functions are essentially super smooth or trivial, almost constant. then they prove that the certain network architectures have an expressivity that allows them to approximate these functions without the curse of dimensionality. Of course, there is no optimization and learning there, but it's a positive result in the direction that there is hope, for example, for anisotropic base of spaces. These are very much axis aligned, right? So this is about smoothness in the first direction, in the second coordinate direction, in the third coordinate direction. So they're not super flexible, but it's very interesting. Judiski and others, Tsibakov and others, have a paper several years ago when they consider the general G composed with H, and they show that there are some surprises. So if you use this structure, you can adapt to it, and if H is smoother than G, then actually using this compositional structure, you gain in the rate of learning capital F. So you get a rate which is better than the one that comes from the smoothness of G, right? G composed with H in general is only as smooth as G. But in fact, if you have this decomposition and H is sufficiently smooth, so smoother than G, you gain a little bit. But none of that avoids the curse of dimensionality. There are other types of compositions. Instead of just two functions, maybe many of them, where each of them only depends on a few variables. So maybe your high dimensional functions can be written as a long composition of functions which use only a very small number of variables. This is a nice paper by Shen and others. And then you can prove again that you can construct neural networks whose approximation properties scale with n to minus a power that does not depend on the ambient dimension. It only depends on the maximum dimension used by any of these functions. Again, whether you can optimize and get a learning rate, maybe it's a slightly different story, but at least it's hopeful. And then there is even more recent work by Jason Lee at Princeton and others on models where the function h is a low-degree polynomial. And then by constructing neural networks with a spectral structure and training them in a special way to make the features emerge, they claim a sample complexity for learning f, which just scales like the dimension to the p, where p is the degree of a polynomial h, which is also good news. All right, and I'm sure there are more works also in this direction in the paper so this is not quite finished, but the paper we're writing, we sort of overview many of them. All right, so let's talk about a simple model. So the conclusion of this is that, there are lots of open questions about these models G composed with H, and so we start simple. And in a work that hopefully is going to be on the archive next week with my student Yan Tao, we consider the following we introduce and consider the following model. We call it the nonlinear single variable model, where we replace the line in the single index model by a curve. Right? That seems a natural generalization. So there is a curve in RD. There is a neighborhood around this curve. So you should think of this curve as having curvature about 1. You should think of taking a tube of radius about 1 around this curve. And in the single index model, we were taking x and we were projecting it onto the line v. The analog thing in our context is you have x and you project it to the nearest point on the curve to x. This is well defined in this tube around the curve. And then we assume that the function f is a small f of pi gamma of x, with pi gamma of x is the closest point to on gamma to the point x. And questions, under some assumptions on the curve, on the small function f, can we estimate capital F at a rate which is not cursed by the dimension d? Is there an efficient algorithm for constructing that estimator? And we also care about not having constants exponentially in d. I'm sorry I keep saying this, but constants matter, and I see even in recent papers, even on single index, multi-index models, where these constants are now tracked and they're exponential in capital D, making the algorithm potentially not that useful in practice.
Why are you calling it a constant, though? It's not a constant anymore.
Right? I think so. We should really start talking, we have rates, but also there is that big constant there, right? I agree. So these are sort of the specifics, maybe due to the fact that I'm running incredibly late. I'm going to skip on many of these, but the basic picture is the following. There is the curve. There is the random variable x is distributed sort of around the curve. It's not close to the curve, right? It's not just a noisy version of the curve. The noise is big. It's order 1, right? And every x can be written as a correspondingly random point on the curve plus a correction orthogonal to it, to this zd minus 1. And think of this zd minus 1 as bounded or sub-Gaussian or something like that. And this is a projection of one such curve. This is a curve in 36 dimension, inspired by the Meyer staircase. That's Yves Meyer. I couldn't find a reference. I know that he introduced these sort of constructions where you take, say, an arrow Gaussian and you translate it, and you look at this as a subset in L1 or in L2, depending on the regularity, or in LP, depending on the regularity you want to get. And then maybe you take limits as this Gaussian becomes narrower and narrower. And so you see that when you translate this Gaussian, you quickly explore orthogonal directions, or almost orthogonal directions, because the Gaussians become almost orthogonal after a few sigmas of translation. And so this curve really curves around in many dimensions. And we do a variation of that, which is even harder. It curves even more. And when you project it down to any low-dimensional subspace, it always looks like something like this. So this is the curve going around. These are our points, which are all one off of the curve, and they're colored by the value of the function. So we're interested in curves that when you project to low dimensions, you get things that you cannot regress, right? This is many to one, right? So these are complex curves, complicated curves. But we like inverse regression. We look at the gradient of a function f, and it's something times the tangent to the curve at the point closest to x, right? And so we can hope to play a similar game using inverse regression, because then the gradient of this function is giving us information about the curve. And the game is going to be similar to the previous algorithm. Let me just, okay, let me go through that at this stage. So we partition the y into intervals. We look at the pre-images. We hope that those look like thin slices of this tube, which are thin in the direction orthogonal to the curve, and whose shortest direction is in the direction of the local tangent to the curve. So we look at the geometry of each slice, just for the first two moments, mean and covariance. We'll approximate the closest point projection, the pi gamma x, that takes every point and projects into the nearest point on the curve by using mean and covariance of the slice. And then we project locally, and we try to learn the function f. Note that here we cannot average these tangents everywhere. We cannot gather strength across all our samples globally, which really help defeating the curse of dimensionality in the single index model. And so we're a little bit worried about whether we're going to be able to avoid the curse of dimensionality in this case. So here are two slices of that function that I showed you before, and they look like the way we like them. So this is one slice in blue and another slice in green. We have more points than this. We only plot 2,000 of them, and the mean is pretty close to being on the curve, and the shortest singular vector is about in the direction tangent to the curve, both of this slice and this slice. And if we look at the singular values of the covariance matrix of each of the slices, blue and green respectively, lots of singular values are large. So we're plotting the largest, the second largest, the mean of all of them, and then the second smallest and the smallest of all of them. So there is a big gap between the smallest one and all the others. And so, this is the good direction to pick. Unfortunately, we're not always in the same situation. In the very same example, we look at two other slices, and they look like this. They're actually now long along the direction of the curve and thin normally to the curve. Oops. So then here, the means are still on the curve, but the direction that we want is the largest singular vector, and so on. But if you look at the spectrum of the covariance, that's enough to distinguish between the two cases. So while in this case, the biggest gap was around the minimal singular value, here the largest gap is around the largest one. And so we can tell these two cases apart, thin slice versus wide slice. And so we have an algorithm that does the same steps sort of that I just described. So you slice in the y direction, you compute basic geometry, mean and covariance structure of each of the slices. You decide whether the slice is thin or wide, and you change the metric of the space locally and introduce a sort of Malanobis distance that is telling you in which direction to project in order to get the closest point to the curve. And then for every new point, you need to decide in which slice you are. So we build a slice classifier. Here I emphasize this because in NVIDIA's talk there was a discussion about classification versus regression. Here for us, this slice classifier is crucial. A point comes in, and we need to decide in which slice to put it, and this curve is curving around. So we have all these different Malanobis distances, one per slice, and we need to decide which one to use in order to do the projection. So there is a classification text there, which is crucial for us, because once that is done, we project on the curve, and now we are in 1D and learn. Yes,
So,
yeah.
so it seems like there's, whether you're in a wide or a thin slice is going to depend on, like you can no longer say whether a slice is going to be small just by looking at y. It depends on the curvature of the curve.
Curvature of the curve, gradient of the function, kind of bigger and smaller, thicker.
Yeah, so
exactly. So this problem is really multi-scale. We need to decide the size of the slices here, and then of course also after the projection of the curve, we need to decide the scale there, but choosing the scale of the slices is crucial.
But does it help to look at multiple scales of slices at the same place? As a way, if you just track these singular values and when the biggest one is the right one and the smallest one, it should give you some estimator of something interesting happening to the curve and the function.
Yeah, that's great. So yeah, that's fantastic. And it does, but those are the plots that we look at all the time. However, the theorem that we prove tells us how to choose that scale precisely, but it's because in the theorem we assume that we know or we have a bound on the curvature, on the gradient of f, and so on. If we didn't have those bounds, we would look across scales and say, oh, look at this. The singular values go from, one big gap over here to one big gap over there. Let's use this multi-scale information. That would be, I feel, really the good way to go if we didn't make this assumption of knowing bounds on curvature and gradients. Yeah. And so what can we prove? This is the informal statement. So our mean square error against the function capital F is going to have one part which scales optimally as if we knew the curve, as if we were in one dimension, right? N to the minus 2s over 2s plus 1. I'm sorry, there is a 2 in the numerator now because I'm looking at mean squared error. I guess in my previous results I was looking at the L2 error, not squared. But we also have an additive term, which is about the size of the noise in the y's. So sigma is, say, the sub-Gaussian norm of the noise that is corrupting the y values to a certain power. And we cannot kill this residual noise. Maybe I'm being too specific, but this actually bugs me. We think we know of ways to go around this, but they are really messy, both in theory and from the point of the algorithm, and so we haven't done that yet, and we don't plan to do it in the paper that we're going to put out hopefully next week. Now we have big assumptions. F is all, the function f on the curve is all the rest, and it's still roughly monotone. Again, this is the big assumption I would love to get rid of by maybe clustering these slices in the non-monotone case. Gamma only needs to be seen 1, 1, so definitely we're not assuming smoothness increasing with the dimension. And then other natural assumptions, the noise shouldn't be too large. The constants are not exponentially the dimension. The worst one is d to the 4th, and maybe it could be reduced to d to the 3rd. We haven't optimized that. The algorithm runs in a log n d cube. All right, so you get your answer quickly. Yes?
Do you know what the lower bounds are? You kind of feel you can get rid of this sigma term, but you know that...
Okay, so there was no additive term here. This rate is min-max optima in one dimension, so this cannot be beaten in the min-max sense. And for us, it's sort of the first example of a model where G and H are both nonlinear, and we estimate them both, and the estimate of both is not cursed by the dimensionality, and there is a fast algorithm and no exponential constants anywhere. Okay, I'm not going to go through roughly monotone is what maybe is the thing that we want to get rid of the most. I'm not going to go through the statement of the theorem. We do this just because there are no constants that depend on capital D exponentially, the worst 4th power. So here are plots of the MSE as the dimension increases, and after, as a function of the number of samples. So after the number of samples is about d squared or d cubed, we get nice convergence. So they move, so as you go this way, the dimension increases, so the curves go to the right. We do need more samples as a function of d, but only a lower order polynomial of them. Okay, and after that we get convergence. And these are the similar plots, but for the estimate of the centers, so these points on gamma, this we get the parametric rate, we prove, and it's of course numerically verified. And we also get the parametric rate for the estimation of a tangent vector to the curve. So these are all 1 over square root of n. Oh, and if we have no noise, we have a theorem that shows we get very nice convergence. Say the function is Lipschitz, the convergence is of the order 1 over n squared. So the interpolating regime is really good, completely dimension independent and really fast. All right, so in the 6 minutes I have, the second part of my talk, 3 papers. All right, so this is an ongoing collaboration with Natalia Trajanova and their lab. This has been really an honor and fantastic for me. She has been working on models for the electrophysiology of the heart for decades, where a patient comes in, an image of the heart of the patient is taken by a special type of MRI that emphasizes some of the possible features of your heart, of what is not working there, scar tissue. And from those images, in our lab, they construct digital twins of that heart, and they electrically stimulate the digital twin to see if there are types of stimulations at certain locations and at certain frequencies that are dangerous for the patient. And if they find them, they try to identify the spot that should be ablated, burned by a surgeon, in order to avoid those patterns. And these models are very expensive to compute with. They're built at a very high resolutions with millions of boxes, millions of finite elements. The equations are PDEs, reaction diffusion type of PDEs, with a reaction term that depends on a bunch of ODEs, which are modeling electrical, which are modeling ion channels at the almost cellular level. And so the system of ODEs is about 20-dimensional in some of these models, and it's coupled with the PDE through the reaction term in a reaction diffusion equation. So these things are expensive to compute. I think they are the biggest users of the Maryland cluster for doing these computations. So lots of problems here, and machine learning, I think, can help, and I've tried to help them in some of these issues. So this is the applied part of my talk. So in one of the first works with Natalia and Dan and many other collaborators, we looked at the problem of just segmenting the heart. When you get these MRI scans, I look at them and I'm like, where is the heart? So I got trained, and then we decided to train an algorithm for doing the segmentation of the heart and the myocardium, which is just the thick surface around the heart, the muscular part. And so we construct a network. The network architecture, maybe I'm not going to go into the detail with. Maybe the only cute thing that I want to remark here is that we really care about segmenting the myocardium in a way which is anatomically correct. We don't want to segment and get a heart which is a hole at the bottom just because when we do the MRI, the slices that we had missed the closure of the heart at the bottom. And so we do some probabilistic modeling in an autoencoder, in the range of an autoencoder, so that we rule out anatomically incorrect segmentations. And that does help, all right? This has been a lot of work on some of the largest data sets of hearts segmented by hand and so on, so that we could train our algorithms in order to detect both the myocardium and the dangerous parts, which are scars in your heart that can form during your lifetime and can really affect the propagation of electricity on the heart. All right. The second project I wanted to briefly talk about is the following. And so this is, again, of course, with Natalia and Dan and Julie Shade and many others. So we say, well, now we have these cardio MRI images. Maybe we have some clinical data for every one of the patients. Can we predict the risk as a function of time of having a bad event, in this case, sudden cardiac death? And so this is a network that acts both on the images and on clinical data. These are two separate networks that then we merge, and they output a probability of probability of having events as a function of time. And so maybe after a certain time, you are more likely to have an event, and that might increase up to the time and decrease after that. And we get risk curves, and that we test on both, on patient data that comes from multiple hospitals, collected from multiple MRI machines. In fact, some of this data has been used all in testing in order to try to check that our algorithm is robust and transferable to different hospitals and different machines. And we also try to interpret the results of our network. So first of all, our network, just by looking at images, seems to perform better than existing risk classifiers based on images and or clinical data. Our network, when it uses both images and clinical data, is better than the one that only uses images. And then we also try to interpret what this network is looking at, computing gradients of these networks, and looking at which parts of the heart they get emphasized and which clinical variables get emphasized. And by doing this analysis, we'll just discover that the network is not just doing trivial inferences, for example, looking at how big this car part of the heart is and use that. It actually uses location. It actually uses dependencies between those locations and other clinical correlates. So it's actually seems to be doing non-trivial work. I'm not going to talk about the risk assessments, measures, and so on, but I refer you to the paper for all the details, which are, these things need to be done in a statistically very careful way. And maybe the last thing, which is back to composition of functions, which was supposed to be the theme of this talk, is the following. This is a recent paper. It's on the archive, but it just got accepted to Nature Computational Science with Natalia and Ming Hin. And here the problem is the following. Every patient comes in, the patient gets scanned, and every patient has a different heart. We want to solve a PD on that heart, and so we have a family of PDEs on different domains. And every heart has different features. For example, the fibers on that heart might be patient-dependent too. And so how do we solve families of PDEs on different domains? And we do something very, very natural. So we have different domains. Think of hearts of different patients up here. And on each of them, we have a PDE, so with some initial condition, and then it evolves in time under some operator, which is domain-dependent. Well, we take these domains and we map them to a canonical domain. And when we move the PDE with the diffeomorphism, when we move the PDE that we had on the patient-specific heart to the canonical heart, the PDE changes. And now this diffeomorphism has become a parameter in the PDE on this canonical domain. It's an infinite dimensional parameter, but we have ways of compressing it. And so we have a way then of learning how to solve a family of PDEs parameterized by initial conditions, boundary conditions, and the diffeomorphisms that led to the canonical domain, and predict solutions. And once we predict the solutions, of course, we can invert the diffeomorphisms and go back there. So this is really using compositionality with the diffeomorphisms that take us from the patient-specific heart to a canonical heart. And we do this for simple equations, like the Laplace equations. The accuracy we get is about 3 digits. And this is the Laplace equation with non-boundary conditions on the form squared. The form squares. All right? And so the diffeomorphisms are estimated from data. We don't assume that we know them a priori. And we do reasonably well in generalization. This is a reaction diffusion equation on an annulus that gets distorted. And for these equations, we get about 2 digits. And then the applications to the heart, where we have these reaction diffusion equations, where the reaction term doesn't depend just on U, which is the electric potential on the heart, but also on V, which are these high-dimensional parameters that are driven by an ODE. So that's the coupling with a high-dimensional system of ODEs. And there is a little bit of fast law here, but the ODEs are not really fast compared to the evolution of U, so it's not clear how much averaging homogenization here could help, but it's something that we're looking at. And here are some beautiful pictures of these hearts. You start with the images, you reconstruct the digital hearts. These are the universal hearts that get then, you have different initial conditions because you stimulate them in different ways. And we decided here to predict 2 things that we think are clinically relevant. Instead of actually predicting solutions of the PDE, we predict the first activation time. So at every point in the heart, you ask when is the first time when an electrical wave started at some other location reaches that point. And the second activation time, the wave goes through and then maybe comes back. And so these are the 2 functions that we try to predict. They're relatively smooth, and we have a prediction error, which is in the 1.5 to 2 digits of accuracy. And we hope that that might be sufficient for at least some of the applications. I'm going to talk about graph-free neural kernel. The paper just appeared on the archive. This is joint work with Shane and Zen, and where we generalize Fourier neural operators to graphs and manifolds, which are tuned to the mesh that we have, but also to the PD that we're trying to solve in order to do better predictions for solutions of PDEs, actually integrated in times with when the amount of data is not very large. These are some results on hearts. And thank you for your attention, and sorry for going over, but I did get several questions during the talk, which I appreciate.